Hey everyone, this is video 533. In this video, I'm going to go over how to find the capacitance of a cylindrical capacitor. Cylindrical capacitor consists of two concentric conducting cylinders. Just like the spherical capacitor, the inner cylinder can be hollow or solid. So let's take a look at how to find the capacitance of this capacitor. So we're going to follow the same steps that we did in the previous two videos. We're going to find the electric field, then the potential, and then the capacitance. So the first thing is we need the electric field here in the region between the two cylinders so that we'll be able to find the potential difference. To find the electric field here in between in this region, we can use Gauss's law. So let's write down Gauss's law, E dot dA. If you don't have it memorized by now, probably should. Charge in over epsilon naught. And we talked about when we have cylindrical symmetry, we have a cylindrical Gaussian surface, and the field is going to be parallel to the area vector. So the left-hand side will simplify to E times 2 pi RL. And then the charge enclosed is just going to be capital Q. The charge of the inner conductor is Q, the outer one is negative Q, over epsilon naught. So the electric field is going to be Q over 2 pi epsilon L, and then we can say 1 over R. And we can give it a direction just like with the sphere. It's radial, pointing outwards. And then the next thing is to find the potential difference. Let's do it a different color here. So delta V, since the field is non-uniform again, we have to integrate negative E dot ds. And just like before, the previous example with the spherical capacitor, E dot ds is going to simplify to just EdR because the field is radial. And we're going to get that radial component for ds. So we're going to get the integral of this. Let's go ahead and take the constants out of the integral. So negative q over 2 pi epsilon L. And then inside the integral, it's just going to be 1 over r dr. And we're going to integrate from a to b, the inner radius to the outer radius. And when we do that, we're going to get all of these constants here, negative q over 2 pi epsilon L. And then the integral of 1 over r is the log. So we're going to get log of b minus log of a. But log of b minus log of a is just going to be log of b over a. So there we have it, the potential difference. And once again, we just want the magnitude of the potential difference. So we can just get rid of this negative sign here. And now we are ready to find the capacitance. So the capacitance is going to be the charge per the voltage. So we're going to do Q, and instead of dividing, we are going to multiply by the reciprocal. So 2 pi epsilon L over Q log of B over A. And we notice that the charges cancel out. And so we have our answer for the capacitance of a cylindrical capacitor. C equals 2 pi epsilon naught L over log of B over A. So for all three examples that we did finding the capacitance, parallel plate, spherical, cylindrical, the capacitance of the capacitor just depends on the geometry. In parallel plate, it was the distance and the area of the plates, the distance between the plates. For the spheres, it was just depending on the radius of the spheres. For the cylinder, it's going to depend on the cylinder dimension as well as the length here. So that's very important to remember that capacitance does not depend on charge and voltage. just depends on the geometry.